Alright, thanks for watching. And today I would like to talk to you about the ultimate test for diagonalization. Namely, there's a very good test that works when everything else fails to check if a matrix is diagonalizable or not. And so here it is. Namely, so today I will mainly do it for linear transformations, but everything else works for matrices. So suppose if T or A, so a linear transformation from a finite dimensional vector space to itself, or an n by n matrix, has eigenvalues lambda 1 up to lambda k with corresponding multiplicities. And I'll define all those terms, so don't worry. Multiplicities. Cities m1 up to mk. Then it's very easy to check if T is diagonalizable. Just check if the eigenspaces are as big as possible. So if and only if for all I equals 1 up to k, if you take the eigenspace corresponding to lambda I, it's equal to mi. I'll give you an example again illustrating all those things. And alright, in other words, so if a linear transformation is diagonalizable, then the eigenspace is as big as possible. And conversely, if for some eigenvalue the eigenspace isn't optimal, then the matrix or the linear transformation is not diagonalizable. And again, this is really the ultimate test for checking if something is diagonalizable, and that's if everything else fails. And what do I mean by everything else? Because there are certainly easier tests. First of all, if the characteristic polynomial of T doesn't split, so it's not a product of linear factors, then you can conclude it's not diagonalizable already. Second, if you have, let's say, an n by n matrix and you get n different eigenvalues, then also you can conclude that the matrix is not diagonalizable. But here it's really if everything else fails, you have to use this test. And in this video, because otherwise it will take an hour, today I will only show this part. If the eigenspaces are as big as possible, then it's diagonalizable. So for example, just to illustrate, is the following matrix diagonalizable? So 1, 1, 1, 0, 1, 0, 0, 1, 2. Is this diagonalizable? Well, let's see. What this says is that we need to check that the eigenspaces are as big as possible. So first of all, let's calculate the characteristic polynomial of that matrix, which is defined to be determinant of A minus Ti, which just means you subtract T from the diagonals. So 1 minus T, 1, 1, 0, 1 minus T, 0, 0, 1, 2 minus T. And then if you calculate this, so this becomes 1 minus T times the determinant of 1 minus T, 0, 0, 2 minus T. And if you want, that becomes 1 minus T squared times 2 minus T. First of all, what's nice is, and again this is necessary, I didn't really write this in this theorem because I assume it's true. Notice here the polynomial is just a product of linear factors. And this is what we call it splits. We don't have stuff like t squared plus 1, for example, in the real numbers, which cannot be written as a product of linear factors. So it does split, and moreover, you can find the eigenvalues. So the eigenvalues here are lambda 1, which is 1, 1 and lambda 2, which is 2. Okay, now, what are those MKs? MK is just the number of times this eigenvalue is repeated. So here, because 1 is repeated twice, the multiplicity is 2. And here, because 2 is just repeated once, the multiplicity is 1. And what we need to show is essentially this. In order for it to be diagonalizable, it's enough to show that for this eigenvalue, the eigenspace is two-dimensional, and for this eigenvalue, the eigenspace is one-dimensional. And well, let's do that. And here's the definition of the eigenspace. So E lambda for a given eigenvalue is just the set of x where ax equals lambda x, which is really the same thing as the null space of A minus lambda I. So for E1, let's find the null space of A minus I, which you can get by setting t equals to 1 in the stuff that I erased. But if you do that, you get null space, I think, of 0, 1, 1, 0, 0, 0, 0, 1, 1, and then you can just row reduce to get the null space of 0, 1, 1, 0, 0, 0, 0, 0, 0. And here's the cool thing. You never actually have to find what that eigenspace is. You just need to check if the dimensions match. So, first of all, how many pivots are there? Well, there's one pivot. And what does that mean? It means that without even finding the null space, you know that the null space is two-dimensional by the rank nullity theorem. The number of pivots is the rank, so we know the rank is 1. So the null space is 3 minus 1, which is two-dimensional. So dim of E1 is then 2. So if we solve this equals 0, you get a basis of two vectors, which matches precisely the multiplicity. And turns out for E2, it's also true. So if you want to similarly check, well, let me remark on that. Check that E2 is one-dimensional. And that's precisely the multiplicity of the eigenvalue. So because the eigenspaces are as big as possible, it follows that T is diagonalizable. If you somehow find, but that's part of another video, that E1 is just one-dimensional, even though it's supposed to be two-dimensional, you can conclude that A is not diagonalizable. And by the way, we actually didn't have to check this because lambda 2 is an eigenvalue, we know that E2 is non-zero. And it turns out E2 can, E2 can actually never be bigger than the multiplicity. So because E2 is at least one-dimensional and at most one-dimensional, E has to be one-dimensional. So there's actually nothing to check here. Okay, and before I prove this, let me kind of explain heuristically why this works. Because suppose you find a basis. I mean, what does it mean for something to be diagonalizable? It means you have to find a basis of eigenvectors. So why this works? So it turns out we can check. And if you're bored, you can do this. We can check that beta 1, which is 1, 0, 0, 0, 1 minus 1, is a basis of E1. And beta 2, for the null space, by the way, here E2 is the null space of A minus 2i, if you want to check that. And it turns out if you do 1, 0, 1, is a basis of E2. Now, in general, if you put two bases together, there's no chance that the whole thing is a new basis, but it turns out here it is true. And well, we'll show that. So it turns out that if you put beta 1 and beta 2 together, there's no debate about this, that all this whole set, so this huge set, which happens by putting all those two together, this thing, it's a basis for F3. I guess R3 in this case, of F3. Which means we are done. We found a basis of eigenvectors, which means that A is diagonalizable by definition. So this is the cool thing. And for the rest of today, or I guess for the rest of this video, let me just show why this is true. And it's all based on a very quick lemma. So if lambda 1 up to lambda k are distinct, and Vi are corresponding eigenvectors, so eigenvectors or the zero vector, because technically zero vector is in this space but not an eigenvector, for I equals 1 up to k, then if the sum of the VI's is 0, it turns out all of them are 0. Vk is 0. Which is a very strange property to have, that if you sum everything and you get 0, the only way to get this is the 0 vector. And if you know direct sums, that's like one of the properties of direct sums. But for now, just think of it as kind of an analog of linear independence. Linear independence tells you if you have some combination that gives you the 0 vector, then it's a trivial combination. And it is true here. So, except here the combinations are vectors, they're not scalars. And why is that? The proof is very neat. So suppose one of the VI's is non-zero. Vi is non-zero, and what do I want to say? So suppose Vi is non-zero for some I. What is that saying? It says that we get a non-trivial linear combo of V1 up to Vk that gives you 0. I guess one thing I have to say, so suppose Vi is not the 0 vector, then you can just eliminate 0 vectors from this whole set, because the sum is still unchanged. So assume all of them are 0. So with a lot of generality, assume all of them are non-zero of the Vi are non-zero. Because again, otherwise you're just adding 0 vectors. So basically, by eliminating 0 vectors, assume all of them are non-zero, then because Vi is in that set and it's non-zero, we know that VI's are eigenvectors. So Vi are eigenvectors. Corresponding to lambda I. Then what do we get? Then we get a non-trivial linear combo of those things. Then get non-trivial linear combo of VI's that gives you 0. And essentially what I'm trying to get at, we get that this whole set is linearly independent. So v1 up to vk is linearly independent, dependent. But this contradicts the fact that they're actually supposed to be linearly independent, because there's another video that I've done where I've shown that eigenvectors corresponding to distinct eigenvalues are linearly independent. So because we find this is linearly dependent, but we know it's linearly independent, we get a contradiction. Contradicts facts. v1 up to vk is linearly independent. And again, see other video, which I'll try to put on the description if I remember, okay. Alright, so, and you'll see this lemma will magically sort of help us. So now let's prove our, theorem. So proof of dimension E lambda I equals mi implies T diagonalizable. And essentially all we need to find is some basis consisting of eigenvectors of T. So a basis of your vector space consisting of eigenvectors of T. And here's how we do it. And by the way, so assume there are only two eigenvalues here, because otherwise the proof is exactly the same. It's just notation-wise it gets very messy. So if for eigenvalues lambda 1 up to lambda k, you have that the eigenspace equals in dimension to the multiplicity, then T is diagonalizable. So suppose k equals 2. And so what this means, T has eigenvalues. Lambda 1 and lambda 2. But here's the thing, so E lambda I, and I like to remind you again in case you forgot, E lambda is just, for the operator case, it's a set of vectors V, such that T of V is lambda V. This is actually a subspace of your vector space. So in particular, we can find bases. So let beta 1 be V1 up to, how big is it? Well, the dimension is M1. So Vm1 be a basis of E lambda 1. So I'd like to remind you, dimension of E lambda 1 is M1. And beta 2, which is W1 up to Wm2, be a basis of E lambda 2. So this is the analog of the two bases I gave you for the other matrix. And all we want to show is if you put both of them together, you actually get a basis of our vector space. So before it was Rn, and now it's just an arbitrary vector space. So claim beta, which is beta 1 union beta 2, is a basis of V. And here's the cool thing. It turns out, how do you show something is a basis? You have to show it's linearly independent and that it spans. But it turns out you don't actually have to show that it spans just by a counting argument. So note, beta, how many vectors does it have? Well, M1 plus M2. M2 vectors. And here's the cool thing. If you add up the multiplicities of all the eigenvalues, you actually get the dimension of the space. So remember we had, for example, that characteristic polynomial, t, I guess 1 minus t squared times 2 minus t to the 1. Well, if you add the multiplicity, if you want the coefficient, the powers here, you get 2 plus 1, which is 3, but it's precisely the dimension of R3 or F3 if you want. So this thing has n vectors, where n is the dimension of your vector space. So if you have a linearly independent set with n vectors, then you get a basis. So all we need to show is that beta is linearly independent. Alright, and let's show this. And you'll see, it's a very beautiful proof. So suppose we have a non-trivial linear combo of all those vectors that give you 0. So suppose a1v1 plus dot 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 plus am1 vm1 plus b1w1 plus dot 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 plus bm2 wm2. It gives you the 0 vector. Then notice what this is saying is somehow the sum of two vectors is 0, because let's define this. Let's define this to be v. Now, we know all the vi's, they're in E lambda 1, but E lambda 1 is a subspace. So if you take any linear combo in the vectors of this subspace, it's still in the same space. So what it's saying is this left vector is in E lambda 1, and this right vector, it's in E lambda 2. So what do we get? We get that the sum of v and w equals 0, where v is in E lambda 1 and w is in E lambda 2. But now we can use our lemma. The lemma says if you have the sum of bunch of vectors, each in a distinct subspace, in a distinct eigenspace, then each of those vectors has to be 0. So by the lemma, v is 0 and w is 0. What is that saying? It says that a1 v1 plus dot 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 plus am1 vm1, it's 0. But remember that beta 1 is a basis. v1 up to vm1 is a basis. So in particular, it's linearly independent. So you conclude that a1 equals 0, dot 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 am1 equals 0. And similarly, because w equals 0, you conclude that all those coefficients are 0, because beta 2 is a basis. Equals 0 up to bm2 equals 0, since beta 2 is a basis. So what can you conclude? You suppose this humongous linear combination gives you 0, and you actually shown that each of those coefficients are all 0. So in particular, this huge set beta is automatically linearly independent. So it is not a surprise that if you basically take all those eigenspaces together, you actually get a linearly independent set. And therefore, beta is linearly independent. It has enough vectors to form a basis of v, and therefore it is a basis of v, and we found a basis of v consisting of eigenvectors of t, and that's just a definition of diagonalizable. Okay, so it's a very, as I said, beautiful proof. And you may ask, well, how did we really use the fact that the eigenspaces are as big as possible? If one of the eigenspaces isn't optimal, then we don't really have this fact anymore. Beta would not have enough vectors for it to be diagonalizable. And then that's a very sad thing. But luckily, if this is true, then it is diagonalizable. All right, I hope you like this little diagonalizability extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.